G'day chemists, welcome to my shed, and yeah, let's talk about reversible and non-reversible reactions. So our learning goal here is that you should be able to define reversible and irreversible or non-reversible reactions, but you'll know you can do this when you can turn it into a table that compares those two ideas right next to each other. So this is your vocabulary. If I could just get you to pause the video here, write this down so you've got this to refer back to as we move through the lesson. Now, there's a new word here called dynamic equilibrium that I want to explain before we move on. So just so you know, dynamic equilibrium is a reversible reaction as it exists in a closed system, which means matter can't leave. Energy can, but matter can't leave or enter. And when we say the forward rate of reaction equals the reverse rate, we mean that they're going backwards and forwards and there's no continuous change. So the rates are the same. The concentrations aren't the same. For example, there might be more products than there are reactants, or there might actually be more reactants than there are products, but the concentrations become stable. There's still movement between the two. It's going backwards and forwards at the same time, but they're happening at exactly the same speed. So any net change is non-existent. So the concentrations stay the same, even though there are things moving from reactants to products and products to reactants. All right, so let's get forward and move into it. So a reversible reaction. We're going to start here with our Haber process, where we've got 3 hydrogens plus 1 nitrogen molecule turns into 2 ammonia molecules. Now, one of the things we need to know about reversible reactions to start off with is that they proceed in both directions. So the reaction is moving forward in this way. So there will be 3 hydrogen molecules bumping into some nitrogen molecules and then turning into 2 ammonia molecules. But at the same time, there'll be 2 ammonia molecules which are decomposing into a nitrogen molecule and 3 hydrogen molecules. So if these guys are at a dynamic equilibrium, they're doing that at the exact same rate and the concentrations are staying the same. They don't have to be the same, but the concentrations are staying the same. Like they're staying constant. So reversible reactions, they don't have to be at dynamic equilibrium. So this could be just reversing backwards and forwards. You could be having lots of reactants and then moving to having lots of products and then backwards and forwards, whatever, depending on the situation. So reversible reactions are denoted by the double arrow down here, not just equilibrium reactions, but reversible reactions. The reaction will reach equilibrium if it's in a closed system. So if it's in a closed system, it will reach its own equilibrium eventually. Some will do this very rapidly, some will do this over time. So usually products from both sides are present in the reaction vessel. In other words, we have products from the forward reaction and products from the reverse reaction. And we'll have these present in like both of these will be present in, especially in a closed system, for a reversible reaction. Now, this will not reach completion except under extreme conditions. In other words, you'll never use up all, again, except under extreme conditions, you'll never use up all of the reactants and have only products. That's what completion means. And completion means that once you've reached completion, these reactants here aren't converting back into the products. As soon as the energy from the extreme conditions change, they'll start going back the way they were. So let's have a look. This here is an open system. It's reversible, but it won't reach an equilibrium. And that's because these particles, they leave and then they don't come back. Whereas in B and C, we have a closed system, right? So it's reversible and eventually it will reach an equilibrium. To start off with, the water here is evaporating. So physical and chemical changes can be reversible reactions. So the water evaporates, turns into a gas, and then it starts to hit here and it bounces, and then it'll go back down. And eventually, it will be the exact same rate forwards and backwards. So we won't notice any change in the water level. Now, non-reversible reactions. So with our non-reversible reactions, it's important to notice that they're not the same as reversible reactions, even though we can reverse them if we put in a ton of energy. Remember, a reversible reaction just has to get over that activation energy. And once that's done, once it's over that activation energy, it's then able to go backwards. But it takes a lot of energy to get backwards. So, for example, a non-reversible reaction is the combustion of magnesium. Here we have two magnesium atoms and we can combust it with one oxygen molecule, so O2, and that will give us two, and these will be a solid, magnesium oxide molecules. And reactions that are non-reversible proceed unidirectionally. In other words, they proceed in the direction of the arrow. And these guys are denoted with just a straight arrow. It's really tempting to think of some reactions as reversible now that we know about it as an idea. For example, photosynthesis, if it goes backwards, turns into respiration. But that's actually an irreversible reaction or a non-reversible reaction because it uses a lot of energy to get it in, or it would use a lot of energy if it wasn't for the catalysts in chlorophyll to get it to go from the respiration backwards to photosynthesis. Reactions reach completion. So a non-reversible reaction will reach a completion either in a closed system or an open system. It will not reach a dynamic equilibrium. In other words, until the limiting reagent is found, it will use all of the components up and move towards the products, and it won't go backwards. So, and if we leave it alone in a reversible reaction, it'll start moving back in the other direction, whereas a non-reversible reaction will not do that. It takes a lot of energy to make them go backwards. So combustion, photosynthesis, precipitations tend to be, but if something is a saturated solution, it will exist as in an equilibrium eventually. Non-reversible reactions often involve state changes. Not always, but they often do. Hope that made a lot of sense. If you have any questions, put them in the comments below and we'll get back to you as quick as we can. Thanks for watching. Don't forget to subscribe, hit that bell, and yeah, we'll see you next time. Bye now.